It's 2 minutes past 2, and we are starting our colloquium, the second colloquium of this year. Today's speaker is Professor Ramon Oliver from University of the Balearic Islands, Spain. Ramon received his PhD in physics in 1993 on prominence oscillation from University of the Balearic Islands, Spain. He then joined as a postdoctoral fellow, University of St. Andrews, Scotland. After completing, he came back to the University of Balearic Islands, Spain as a postdoctoral fellow again for 2 more years, and then he joined the same university as a lecturer in 1996. Since 2009, Ramon has been a professor in University of the Balearic Islands. Ramon's research topics are quite broad, including statistical behavior of solar activity, magnetic Rossby waves, coronal rain, solar spicules, etc. Ramon has authored or co-authored about 150 publications, and he has given 9 invited reviews, and he has advised 15 students for PhD as well as master's thesis. Today, Ramon Oliver will be speaking on the Hitchhiker's Guide to Coronal Rains. Turn it to Ramon.
Okay, so I can share my screen, yes?
Yes.
Okay. Okay. I guess you can see my first screen.
Yes.
My full screen. Okay, so thanks, Mausumi, for the introduction, and I also want to thank HAO for inviting me to give this talk. As you will see, the title is a bit misleading because I'm not going to talk only about coronal rain. Here you can see the outline. The first part is, yes, strictly devoted to coronal rain. It will be mainly observational, but then in the second part and third part, you will see that coronal rain is sometimes forms, is part of broader phenomenon. In the second part, I will describe long period intensity pulsations, and then in the third part, I will, second part is observational as well, and then the third part is based on numerical simulations, and then we will meet thermal non-equilibrium. In this part, we will have the physical insight to explain the first 2 parts. So to start, I'm giving 3 slides to give you a context. This is only for people who are not too familiar with solar physics and the sun's atmosphere. In the first slide, this movie you have here is a transition between 2 images. The first one, the more yellow and uniform one, shows the surface with dotted with some sunspots. It shows plasma at 6,000 Kelvin, and then in the other one, you can see plasma at almost 1 million Kelvin. It shows what we know as the solar corona. And as you can see, it's very structured by magnetic fields. The magnetic fields emerge mostly in sunspots. I mean, the most intense ones emerge from sunspots. And above these sunspots, you can see, for example, here, an active region. And then this band here at high latitude in the northern hemisphere, it's also a band of active regions. They are made mostly of coronal loops, which actually delineate the magnetic field lines. So all these loop structures you can see here, everywhere in active regions, they show plasma, or they are caused by plasma which is confined along given magnetic field lines. The question here, of course, is what hits the solar corona? And this is one of the questions that drives solar physics nowadays. The second context is made of, again, it's a movie, but now it's time is changing. It encompasses 2 days. On the far right, you have the same as before, the surface, the photosphere, showing plasma at 6,000 Kelvin. In the middle, you have, well, as you can see, the solar rotation brings to our view some sunspot groups in the northern and in the southern hemisphere. And as you can see above them, when you look at the middle part of the movie, it's taken at 1 million Kelvin almost. And you can see above the sunspots, you can see the active regions as before. And by looking at how much they change in time, you can realize why they are called active regions. On the left, you have another part of the movie, which is mostly sensitive to plasma. I mean, the most dynamic plasma you can see here is plasma at 80,000 Kelvin. And this highlights that the solar atmosphere is multithermal. In this talk, I will often use these two band passes, one at 304 angstroms, the cool one at 80,000 Kelvin, this one here on the left. And then I'm going to use also quite a lot the 171 angstrom passband, which is this one here, showing, as I said before, plasma brought roughly at 1 million Kelvin. Right, the third context movie is this one here. It's a hotter temperature, 1.5 million Kelvin. And what you have seen now is a flare going off in an active region. A flare is a sudden energy release, in this case in less than 15 minutes. And the reason I'm showing you this movie is to highlight that the coronal rain I'm going to talk about in this talk, in this seminar, is coronal rain not related to flares. So you have seen active regions before which have mild activity, and this is the kind of situation I'm going to consider. I'm not going to consider flares as this one in this movie. So let's go to the first part. What is coronal rain? What do observations tell us? Again, we have a movie here. On the left, I will start it now. On the left, we have the hot 1 million Kelvin passband, and on the right, I have the 80,000 Kelvin passband. Let me start the movie, but before that, again, we have active region here on the north, another active region on the south, and then there are these trans-equatorial loops that connect the two active regions. They are clearly seen at the hot temperature, but they are not seen very much in the cool temperature. But then as you let this evolve, there has been an explosion here at the bottom. This is not coronal rain, but what happens next, and which is unrelated to the explosion, is coronal rain. You can see plasma appearing even here at the top of the trans-equatorial loops, and then the plasma appears out of the blue, and it starts to fall, as you can see now, towards one of the feet of the magnetic field lines. The plasma appears at heights of 100 megameters or more, and when it falls, it forms thin and long strands in both active regions and also in the trans-equatorial loops, as I mentioned. It is believed that the plasma, the same that happens in the hotter temperature, the plasma delineates the magnetic field lines. So in the cool temperature, the plasma falls along magnetic field lines. Now, let me start, when talking about the temperature, when talking about the properties, let me start with the temperature. The movie I showed you before has another panel. It corresponds to this rectangle here, the dashed one, and it's shown on the right. And this corresponds to even cooler temperature of almost 60,000 Kelvin. And as you can see, there is a very strong degree of co-speciality of the strands that are formed in the cool region, in the 80,000 Kelvin and in the 60,000 Kelvin. So coronal rain has different temperatures, and it looks very much the same on the different temperatures. There are two paths here, marked A and B, and they will allow later to construct space-time diagrams, of which I will speak later, as I said. So this is a cooler temperature, 10,000 Kelvin, and coronal rain is only seen in this area, but also seen on the disk falling to the surface. And as you can see, coronal rain is a bit different here. Sometimes it forms very long strands, but sometimes it appears very clumpy. The point is that maybe it's clumpy because the material is not cannot emit enough light so we can see it, and it's dark along the strand, right? So after discussing the temperature, let me introduce you to the spatial scales. First is the width. It is shown in these two histograms, they correspond to the same events, but studied with different instruments. And as you can see, you have width here in different scales, horizontal scales, and this is the occurrences. So you can see that there are different distributions of width. And the reason for this is that the instruments used have different spatial resolution. So the finer instrument allows you to see finer widths. And the idea put forward in this work by Antolin and co-workers is that there are possibly a large proportion of coronal rain blobs which are not detected because they are too thin to be seen by this, even the best instrument used in this paper. So coronal rain can be more widespread than we can see. Regarding the lengths, this is more or less what I described before in, say, middle temperatures between 20 and 80,000 Kelvin. Coronal rain, as you have seen in the first movie, forms very long strands. And then in the second movie, in the H-alpha line, at cooler temperature, you can see that coronal rain can either appear clumpy or can form very long strands. And this is described by these two histograms on the right. Right, let's move to the kinematics. There are two issues here. One is the velocity. The velocity of coronal rain can be compiled or measured through the two components, one on the plane of the sky, which can be measured by the displacement of plasma element, and the other one is the velocity component perpendicular to this one along the line of sight, which can be computed from the Doppler shift of a spectral line. With these two components, which are perpendicular, you calculate the absolute value of the velocity, and then you get this histogram with velocity here on the horizontal axis. You can see that it's broadly distributed between 10 and 150 kilometers per second, and it peaks at roughly 70 kilometers per second. This is the total number of blobs used to construct this diagram. And this is the same kind of values that have been found in other works. On their own, these values don't tell us anything. But then when you look at the speed that a coronal rain clump would have when it falls, this speed is much smaller than corresponds to the conversion of potential energy to kinetic energy. So the acceleration is much smaller than that of free fall. Typical values are around or between 10 and 100 meters per second squared, which are smaller than the acceleration of gravity in the solar atmosphere. And of course, this value is not the important one. It is the projection of the acceleration of gravity parallel to the magnetic field, because, as I said before, coronal rain falls parallel to the magnetic field. But still, when you do this projection, you still get values which are much higher than those observed. Another way of looking at this, at the smaller than free fall acceleration, is to compute the space-time diagrams. These are along these two A and B paths I described before. Here you have plots for different spectral lines or passbands. You have distance here or space, and then you have time here. And you can see very clearly that there are two coronal rain blobs here and here falling one after another. They come in different times, and they fall at more or less constant velocity. The sign of an acceleration is a parabolic shape here. So the linear shape tells us that the velocity is constant. Right, to try and understand this, now I'm moving away from observations. I'm going to show you results of two works in which we have done numerical simulations of a blob that is released in an isothermal atmosphere. The first simulation I'm going to describe is one-dimensional, so it's purely hydrodynamic, and the forces that act on the blob are only gravity and the pressure gradient. So on the right, you have density as a function of height. The blob is released initially at 50 megameter height, and then it falls, as I said, under the action of the two forces. The point is that now at 540 seconds, the blob should have reached the z = 0 height. And that means that there is something which is stopping, is breaking the blob. And to see what it is, we can also see, can have a look at the pressure variation. It's the same idea as before, pressure versus height. The red line is the pressure, which is initially exponentially stratified before the blob is released. And the vertical green line marks the blob position from the previous movie. You can see that as soon as the blob is released, the pressure changes. It's the black line now. And a pressure gradient is created that moves together with the blob. And this pressure gradient exactly counteracts, or roughly exactly counteracts the force of gravity. Right, in this case, this simulation is quite artificial because the blob has not formed, so to say, naturally. We have injected it. But there are other 1D simulations in which the blob is formed naturally. And in all of them, I actually analyzed these 3 cases. In all of them, the pressure gradient that I'm mentioning here appears, and also the blob reaches an almost constant velocity. So it seems that the pressure gradient formed at the blob position is quite a robust mechanism to break it. But then this is 1D. In the 2D case, we also have magnetic forces. We have the Lorentz force. So is it important? The idea is to perform the same kind of simulations. You have a vertical cut here of the atmosphere. The vertical range is more or less the same as before. And the blob is circular, but it appears elliptical because of the different scales in the horizontal and vertical directions. Here you will see this dashed red line, which marks the free fall position. You will see the density here. And then these asterisks here, these 5 crosses, mark the position of the rain blob if you perform a 1D simulation with a vertical slice only. So you cut here and do the same numerical simulation I mentioned before, or cut here, here, here at 5 different positions. First thing that calls your attention is that the blob is falling slower than free fall. But then it's very obvious that the V-shaped form appears, and this has not been observed. But maybe the reason is that either this is wrong, but of course it appears in other numerical simulations in which the blob is not injected. But it's also possible that this V shape is not observed because of the wings being too weak. So maybe they are invisible in practice. And the third thing is that the asterisks follow very closely the 2D simulations. So 1D simulations and 2D simulations tell us more or less the same. The pressure gradient is stopping in the same way the 2D blob as it does in the 1D case. Now, more or less, we are sleeping now, so let me make a little joke. This guy, Sheldon Cooper, would put it this way: the 2-dimensional results are more or less the sum for X positions of the 1-dimensional results. Right. Probably some of you have noticed that I have mentioned passbands or spectral lines which correspond to ionized species. So helium ionized 1 time, silicon 3 times, carbon 1 time, etc. And then I have also mentioned 2 spectral lines, or actually only 1, but there is a second line which has been used in coronal rain studies, and they correspond to neutral helium and neutral hydrogen. What we see is that there is a large spatial coherence of the ionized and the neutral components. So we see that the rain blob, the rain strands follow the same path, and they superpose very nicely on each other. So there must be a strong ion-neutral coupling. And here at the bottom, I mentioned a couple of works, but there are many others in which the ionized and neutral components are observed at the same time. So why I'm saying that there must be a strong ion-neutral coupling? Well, here I'm going to show numerical simulations performed by David Martinez Gomez. And in these simulations, you will see on the left panel an inclined magnetic field in which a blob is released. This is the same vertical cut as before, but before the magnetic field was vertical. Now it's inclined. The ions and neutrals are shown with orange and blue colors. So these and these are the pressures, which are separated. But here we have the density together. In the first movie, the friction between ions and neutrals which in principle couples the two fluids, it has been switched off. And then you see that the orange stuff follows the field lines because it's ionized. It's forced to follow the field lines, but the neutral part follows vertically, and it doesn't feel the magnetic field. So let's move to the coupled case. It's the same starting point, but now, as you can see, the two components fall together. So the friction is strong enough to lead us to this situation. Again, you can see that the V shape is present here. You can also see that a pressure gradient across across the blob is also formed. So this blob is quantitatively break by the same procedure as the 1D case, which was fully ionized. Okay, finally, in this part about the observations, I'm going to discuss something related to magnetic field. First, magnetic field lines. Based on the assumption that the plasma moves along the magnetic field, the coronal rain can be used to trace magnetic field lines. So in the left panel, you have the trajectories of, as you can see, a big number of coronal rain blobs. But then these trajectories here are drawn on the plane of the sky. So we don't know whether say, one blob which is falling here comes towards us, maybe falls, but it's moving away from us, or maybe this field line is contained on the plane of the sky. So in this same paper, the angle that these field lines make with the plane of the sky has been shown by colors here. So green means that essentially the field line is contained on the plane of the slide. So these field lines, as we see them, they have no projection effects. The red color means that the plasma is moving away from us. So that means that these field lines, as the plasma is falling, it's coming or it's going away from us. And the opposite for the blue case. So we can study the three-dimensional structure of the magnetic field, but also we can measure the magnetic field strength. In this paper, we computed the two components of the magnetic field with respect to the plane of the sky. So the perpendicular one, perpendicular to the plane of the sky along the line of sight, was inferred from a Bayesian inference in which we use the weak field approximation. And then the other component, the one on the plane of the sky, was obtained from the line of sight component plus the vector velocity, which was computed, as I said before. And then we got this histogram, which is valid for blobs below 9 megameters. Why is this? Because the field of view is restricted to very low heights. So this is valid for an active region at low heights. And what you can see here, this is total magnetic field strength. It varies between roughly 200 and 1,000 Gauss. These values here are not absent. They simply cannot be detected by this method. And then this is only, I'm referring only to the green part, but then the red values, simply they are too large and they don't satisfy the condition to apply the weak field approximation. So this is telling us that there might be higher values, but we don't know them with sufficient accuracy. Right. This is just to give you an idea of coronal rain, but coronal rain is sometimes part of a broader phenomenon, which is called long period intensity pulsations. They were observed or discovered by O'Shea et al. In 2014 using the SOHO EIT telescope at more or less, with images more or less than 1.5 million Kelvin. And they were confirmed later by Froment in her PhD thesis using 6 SDO AIA passbands, which means that there are different images with different sensitivity to different temperatures. In total, they observed many events in coronal loops, more than 2,000. And I will be more specific now in my next slide. In these events, they found that the corona or parts of the corona oscillate with a period between 2 or 3 and 16 hours. They analyzed in these two works events which are on disk, and they didn't find, or maybe they didn't search for oscillations in the cool line, in the 304 line. which is also another passband of SDO AIA. So let me, to explain what long period intensity pulsations are, let me go to the rainbow event in which the 304, the 80,000 Kelvin passband is used. In this study, we took images for 2.5 days with 1 minute cadence. So these are two example images in the 1,171 angstroms, the 1 million Kelvin line, this one here, and the 80,000 Kelvin line here, or passband. And then what you can see is that there is, now this has become smaller, the method that's followed to analyze the data was already laid out in O'Shea et al. 2014. This is the region of interest where pulsation or periodic oscillations are going to be observed or will be searched. And this region of interest is sampled into polar coordinates. So we will have a polar angle here, and then we will have radial distance from the center. You can already see that this is a trans-equatorial loop or loop system connecting two active regions. So this is reminiscent of the movie I showed at the beginning, but it's a different case. And then you can see here that there is an orange line, which I'm going to explain now how it's obtained. And then you can see coronal rain very clearly here in the cold passband. So what the method consists of is in computing for each, let me go backwards. You take a spatial point here, you have the 171 Armstrong variation in time, and you compute the power spectral distribution. And you do that for each spatial position, right? With this, you can construct power maps, power at different Fourier frequencies, like this one here, this one, and this one. The middle one corresponds to 6.7 hours. And here you can see, in all of them, you can see structures which resemble the trans-equatorial loops. I didn't mention that this is the polar angle, and this is the radial distance from the center. So this is the region of interest in the three cases, but now in polar coordinates. So as I was saying, you can see that some structures trace the trans-equatorial loops. Some structures belong to one or the other active region. And the power level, which is shown here, is quite low in the three diagrams, except here, where you can see very strong power concentrated at the top of the trans-equatorial loops. So the orange area is defined as the collection of points where the power exceeds 5 times the local power caused by noise, right? So the idea is to study these 6.7 hour pulsations or periodicity by averaging all the signals that we have in this area. This here, what I'm showing here, is only for the 171 Armstrong, for the 1 million Kelvin, but this is done for the 7 band passes. And then what you got is this plot here. This is time, the 2.5 days, and this is intensity normalized to the maximum value. And then I want to call your attention to the 171, the green line, which is very periodic. So this is the average of the signals in the orange area we had in the images before. Then you can see the orange curve, which is also visually very periodic. It shows plasma, which has a lower temperature, 500,000 degrees. And then you have the 80,000 Kelvin contribution, which is this red line here. So you visually see that there are these periodic changes in three. These are the most clear ones, the three that I've mentioned. And then you also see, apart from this periodicity, you see that the green tends to peak first, then the orange, and then the red. This is not always strictly the same, but normally it is like this. Green, orange, red, green, orange, red. And this is very stable. This lasts for a long time. And this is quite surprising. I mean, when you think of it, the sun has been rotating for 2.5 days. We have selected a region in which there is a long superposition along the line of sight. And then new structures are coming because of rotation, and they are entering in this selected region. And still, this very periodic light curves appear. No? So the idea, and this is confirmed not only visually by looking at this plot, but by looking at the power spectral distribution, the conclusion is that the 6.7-hour periodicity is present in these three temperatures with very high confidence. And then the analysis of time lags and Fourier phase difference between the different signals shows or confirms that the hot pass bands peak before the cooler ones. So what we are seeing is that the loops are periodically cooling from 1 million Kelvin down to 80,000 Kelvin. And then coronal rain appears. So as you can see, there is periodic coronal rain, but if you don't look at the other pass bands, you don't realize that actually the material is coming from locally from the corona, and it is condensing and cooling, right? But still, we don't know where the material comes from, how it reaches the corona. This is another issue, right? But it is cooling locally. So, well, this is the last paragraph is what I said before. This is a very striking situation, right? So we see that coronal rain is the final stage of plasma cooling from, say, coronal temperatures, in this case from 1 million Kelvin. And in the paper by O'Shea et al., this was called the coronal monsoon, because it's periodic, like the monsoons, right? In O'Shea et al. 2018, we have wet monsoons because they produce coronal rain. But in the 3 cases studied by Froment et al. 2015, there was no coronal rain, and for this reason, they are called dry monsoons. So the idea is that we can have long period intensity pulsations, and sometimes they will host coronal rain, but sometimes they won't, right? And this is something we can explain theoretically. Another conclusion here is that not all loops are affected. So we saw that only a bunch of loops, trans-equatorial loops, were affected by this periodic cycle. But this doesn't imply that there is no coronal rain elsewhere. If there is coronal rain, which is isolated, I mean, not in a cycle, or if we have no non-periodic cooling events, which lead to coronal rain formation, these things which are not periodic will not be detected by the method used in this paper. So there is more than only what we have detected here. Right. Well, in this final part, as I said before, I'm going to give you some insight, some physical insight from numerical simulations. And the idea is to ignore the magnetic field, ignore the effects across the magnetic field. That means that if we have a coronal loop, such as the one we have in this cartoon, motions of the plasma are, as I said before, along the magnetic field lines, which are these lines here, right? And also thermal conduction is mostly along the magnetic field. So we can ideally think that one coronal loop is isolated from the neighbors, and then the MHD equations result or are 1D in this case. These are the 3 MHD equations that are solved: the mass continuity, the momentum conservation, and the energy conservation equations. Here, S is the coordinate along the loop, so it's this coordinate here, right? And T is time, of course. Density, velocity, pressure, and temperature are dependent variables in these equations. And of course, there is one more equation, which is the equation of a state, which links density, pressure, and temperature. The shape of the magnetic field is semicircular here, and that is influencing this term here, which is the component of gravity parallel to the magnetic field. So if you want to change the shape of the magnetic field lines or of the loop, then what you have to do is plug in the correct projection of gravity. And finally, A of S, this is a variable that depends on the position along the loop, and is the cross-sectional area, as in this case, where you have A small here and A very large here. Right, in these 3 equations, the main terms that are influencing the numerical simulations, I mean, for the thermal part, are the thermal conduction, the heating, which is this term here, sorry, the cooling, radiative cooling, and this is loss of energy because loops radiate, and this is the way we see them. And then there is a heating. Before, at the beginning of the talk, I said that this is one of the main unknowns of solar physics nowadays. How is the solar corona heated? In this case, how is coronal loop heated? Well, this is a term which is not known, and something has to be done with it. So what I'm going to do here is I'm going to follow cases 3 and 5 of this paper, in which this is the heating profile. It contains two parameters, H naught, which is, let me go to the right. This is a plot of heating, this function H, capital H, versus distance along the loop. So H naught is this offset here, or here, right? And H1 and lambda determine the height of this plateau here. This is the chromosphere, and then lambda determines the rate of decay of this part here and here. The heating is symmetric, and I'm going to consider two cases in which the difference is that H naught is different. All the other parameters are the same. So you can see that the two plots are displaced in the vertical direction. In this case, the loop has a circular shape, and the loop area is uniform. That function A of S I mentioned before. One way of presenting the results are these 4 plots of temperature, density, number density, velocity, temperature, yes, and pressure here, as a function of position along the loop, and then as a function of time. You can see that there is a short transient, and then the loop stabilizes, and we get to a static equilibrium. Another way of presenting the results is by means of contour plots with S here and time here. And you can see the same as before. There is a transient at the beginning of the simulation, and then everything stabilizes and the velocity becomes 0. So let me keep only the temperature. This is case 3 of Mikic et al. 2013. This is the same as before. Case 3, this is the value of H naught, and this is the temperature. So what I'm going to do now is to reduce the temperature progressively. Now, the temperature, no, the parameter H naught. What happens here is that since the heating is becoming smaller, the loop is finally finding an equilibrium with a smaller temperature. So here, the temperature at the top of the loop is roughly 2 million Kelvin, or 2.5, I should say, while here it's only 2 million Kelvin. And this makes sense. You reduce the energy input in the loop, so the loop stabilizes, finds a static equilibrium with a smaller temperature. But then if you reduce further this parameter H naught, and in this case the reduction is very small, it's tiny, it seems that the loop wants to stabilize at a similar temperature, but all of a sudden it blows up. I mean, the temperature goes down very rapidly, and at the same time the density increases quite a lot. And this is called thermal non-equilibrium. The loop cannot reach an equilibrium. And as I said, the change is tiny in the parameter H naught. If you reduce it further and reach case 5, then you can see that the thermal non-equilibrium happens repeatedly, and there are T&E thermal non-equilibrium cycles, one after another, with a constant, more or less constant period after the first cycle. The period stabilizes to a constant value. So let me say a bit more about this. Why is T&E happening? Well, the idea is that in this part of the simulation, the temperature seems to be constant, but actually it's steadily decreasing very slowly. And there is a very steady and slow mass injection from the chromosphere, from the sides, into the corona. So N, the density increases, and the temperature decreases. So let's see what happens with this function here. This is temperature. This is the function Q of T, this one here. And we are more or less at a few million Kelvin. What we see is that as the temperature decreases, the radiative losses, or this function here, increases. So this product increases because both factors increase. So this is bad for the loop, because if it radiates more energy, it will cool. So the temperature will go to the left, and then this term here will increase. It will go up. So the temperature will go more to the left. So what we have in the end, and it happens right here in this very localized time, we have a thermal runaway, which is also called catastrophic cooling. The temperature decreases strongly, very quickly, and the density increases at the loop apex. So this is the formation of a coronal rain blob, which then, as it in time, it will fall down to one of the foot, one of the feet. Right, so we more or less, I mean, we very well understand how thermal non-equilibrium works. Once the blob has reached the chromosphere, what happens is that the magnetic tube is evacuated and everything starts again. So if we run this simulation for longer, we would see another of these catastrophic cooling events. It is better seen in the other simulation I showed before, case 5. You can see that the process starts again and again and again. So these T&E cycles are also called evaporation and condensation cycles. First, material evaporates from the chromosphere into the corona, and then it condenses near the loop apex and falls down. One requirement of T&E is that the heating is strongly concentrated near the loop points, but this is not a sufficient condition for T&E. So a strongly concentrated heating may not lead to T&E. There are other parameters which are important here. And this is just to give you an idea that there are many, many works in which T&E and T&E cycles have been already studied in detail. Something important, the function H is constant in the work I mentioned, but it doesn't need to be constant. If the frequency of the heating events is very large, it's higher than the cooling time scale, then it's as if the heating is constant. Right, so let me try to link what we have seen in both parts, the observations and the numerical simulations. A single T&E event allows to explain coronal rain formation. Then T&E cycles allow to explain long period intensity pulsations, because these are things that repeat, they have coronal rain. Then long period intensity pulsations and T&E cycles require steady heating conditions during hours or days. I said that you can have a very high frequency of repetition of small heating events, but then this heating has to remain, although it can be short, have short variation, overall it has to be very steady, and this is very rare, very striking in active regions. The idea also is that non-steady conditions do not imply that coronal rain will not form. It will not form periodically, but it can form anyway. But still there is more, because here we can explain the wet monsoon, but not the dry monsoon. I mean, here we have seen that we have periodic cycles with coronal rain formation. So let me compare the case 3, which is the one on the left here, with the plot on the right, which is, again, this is the temperature plot as before. The plot on the right is the same as case 3, but now the cross-section of the loop is not constant with height. Here we see, again, T&E cycles. So by changing this thing, we move from static equilibrium to T&E cycles. But the temperature does not reach chromospheric values. It does not go down to, say, 20,000 Kelvin. So these are called incomplete condensations. And then we can see that the wet and dry monsoons can have the same working. They work the same, but in one case, low temperatures are reached, and in the other case, they are not. Now, so far, I've discussed only symmetric configurations, but there is more than this. And then Froment et al. In the 2018 paper did a parametric study for 3 loops with different loop shapes, different cross-sectional area, which are asymmetric. And then they also consider an asymmetric heating, which is similar to the one before, but then there are 2 separate length scales of decrease of the heating in both feet. Then, just very briefly, this is one of their plots. Here you have a grid of 144 simulations in which lambda 1, the length scale on the left foot, is changed, and here lambda 2 is changed on the right foot. Each of these boxes is the temperature variation as a function of position and time. The same plots I showed you before. And then you can see that there are these white dots. They show where there is a complete condensation, what would be a wet monsoon, or an incomplete condensation. And these are actually quite rare in this whole plot. So the conditions to have one of these cyclic behavior must be very, very precise. Otherwise, we have static equilibriums like here, or we can have regions where we have siphon flows. That means that the material is flowing from one end of the loop to the other end. So it's kind of an equilibrium, but it's not static, it's dynamic. So the conclusions from this work is that TNA cycles are found for the 3 loop geometries. I mean, you have similar diagrams, similar grids of numerical simulations, and they all contain TNA cycles. But the position where TNA cycles appear in these grids depend on the loop geometry, and then depend on the heating parameter. And finally, the more concentrated the heating at the foot points, the more likely the loop is to undergo TNA cycles, and in particular, complete condensations, rather than incomplete condensations, due to the high density of the plasma injected in the loop from chromospheric evaporation. So the requirement of very concentrated heating, of course, is recovered here with asymmetric field lines, asymmetric loops. Right, let me finish with one final slide before going to the conclusions. And it's about the conditions for TNE. This was dealt with by Klimchuk and Luna in 2019. And they did many very clever, I would say, analytical approximations. And the aim is to explore the importance of asymmetries in A and H for thermal non-equilibrium to develop. They found 2 conditions. The first is that the heating has to be very concentrated at the feet. This is not new, of course. And they even quantified this with an expression. I'm trying to simplify very much. Instead of showing you the expression, I'm giving you a typical value they found of how much, what does it mean to be concentrated? Well, they reduce it to this figure here. And also another more or less approximate value is the asymmetries in the cross-sectional area between the left and right feet, or the asymmetries in the heating between both feet must not be too great, a factor of 3 when you take the ratio of the left to the right feet. So this is to complete the idea of one condition. Well, then there is another one here. So let me finish with 6 ideas. This is what I would like you to take away. First, long period intensity pulsations are a broad phenomenon, and they can encompass coronal rain or maybe not. So these pulsations can be dry or they can be wet. Thermal non-equilibrium, evaporation and condensation cycles provide a complete explanation of long period intensity pulsations and periodic coronal rain formations. I think there is a very nice link between the 2 things, the observations and the theory. And it's important to emphasize that very stable conditions are required. But then when the conditions are not stable, still we can have coronal rain, which will be non-periodic. Third, TNE is favored by heating concentrated near the loop feet and symmetric configurations. Now let me concentrate more on coronal rain. Regardless of whether it's periodic or not, it brightens coronal loops, and so it allows us to measure their magnetic field strength and also to delineate the magnetic field in the corona. Coronal rain and these long period intensity pulsations can impose restrictions on the active region heating mechanisms. And finally, this applies also to coronal loops that do not host coronal rain. I mean, as you saw in the grid of simulations before, depending on the parameters you have, the same coronal loop will have coronal rain, periodic coronal rain, or may not have it. And both things can impose restrictions on the active region heating mechanisms. Right, so let me finish with, well, I don't want to finish without thanking Douglas Adams for lending me the title of his novel for this talk. If you haven't read it, I really recommend it to you. Thank you for your attention.
Thank you, Ramon, for a very exciting talk. And now we open for questions from the audience. Holly.
Hello, great to see you again, by the way, and thanks for a really great talk. That was wonderful. Regarding the ionization and the coupling with the ions neutrals, The simulation that you showed, was that hydrogen, helium, or it would be interesting to see if there's a difference because the coupling is different for the two, but I didn't know if what you ended up using.
Right, yeah. Yes, it's only hydrogen. Only hydrogen. So it's protons, electrons, and hydrogen.
Great, thank you.
Yeah, it's a good idea to consider helium. Sorry, it's important that we also show that helium follows the neutral helium follows the ionized component.
Yeah, so it probably does, but it'd be interesting to see if there is a difference. I know that the hydrogen is usually it will hold up longer. So anyway.
Yes. Yeah. You're right. Yeah.
Tom? You are muted. We can't hear you. You are muted.
Can you put your question in the chat?
Okay, Tom's question is,
okay,
what is the relation to TZ redshifts and supergranulation?
In relation to supergranulation, I don't know, really. I really don't know. This question has caught me by surprise. I will have to think about it, but I'm sorry, Tom, but I cannot answer your question. Do you expect anything to be there? To have any, to be? I know I shouldn't ask you, but I don't know.
So Tom is typing, I think. And in the meantime, we go to Yuhong. Yuhong?
Yeah, hi. You might have mentioned it, but what determines in your model, what determines that period of the cycle?
Yeah, no, I didn't mention it.
What controls that?
Yeah, there are a few things. I mean, the length of the loop is one of them. And then as you saw, the heating parameters, right? And
the lambda, does it depend on the lambda?
Both, I mean, the three of them, in this model, there are three, H0, H1, and lambda. And also the asymmetries.
Okay.
All of them can change drastically the period.
Okay. And assume your heating is steady. So yes. if you have impulsive heating, that will also, I expect, to change the cycle. You know, it might destroy the cycle, right? If the heating is like intermittent or like, you know, non-steady.
Actually, there are works in which the heating is not steady, it is impulsive, and still they have cycles.
Okay.
So it probably depends more on the amount of energy you give on say, the cooling time scale.
Okay. Okay, I got it. Yeah, that makes sense.
A kind of average, but I don't know. This, to the best of my knowledge, this has not been studied.
Great. Thank you.
Okay, before going to John Bartopel's question, I read what Tom has written. I can't unmute. We see redshifts over the supergranulation pattern on the sun and in unresolved spectra of other stars, only 5 kilometers per second or so.
Right. Yeah.
Okay, we'll go to John Bartopel.
Sorry, maybe short loops. Yeah. So you mean on the? Sorry. now the Spanish word comes to my mind. You mean on the edges of the supergranulation? This is what where you observe the, yes? I have no idea.
So Tom writes maybe short loops.
Mm-hmm. No. I don't know, sorry.
John, and then Piotr.
Yeah, you've got, so foot point heating is involved here. Do you see a solar cycle variability then in coronal rain?
I don't think this has been studied.
Okay.
No, not really. I mean, cycles, I have described one paper by O'Shea et al. 2018, and there are a few other papers which have cycles along one just single observation, but no study about the cycle dependence has been done.
Thank you.
Mm-hmm.
Piotr.
I am ignorant in this area. The first time I've heard about this rain was yesterday when I read about your seminar. I have a question. I noticed that you use compressible equations to simulate those bubbles. Is it dictated by physics or it's a convenience? Like, are those high Mach number flows or low Mach number flows?
They are low. I mean, they are lower than 1. I mean, the ratio of velocity to ascent speed is smaller than 1. Yeah. So, but equations are not incompressible.
No, they were compressible.
Yes.
Yeah, but this is I'm asking, because if you have a low Mach numbers, or then one could use an elastic or glucinesk or whatever. So this is why I'm asking whether it's a physical necessity or whether this is convenience because you have this type of model handy.
Right. They are simply the MHD equations compressible in one dimension.
Thank you.
Mm-hmm.
Gabriel.
Hi. Sorry. So I had a couple of questions. So so when you were showing those V-shaped profiles, is that really is that primarily a density effect? Because basically the edges of the blobs were less dense, so pretty much if you have like a weird asymmetric blob, and that you can have weird asymmetric shapes, and that leads me to my second question is about the size of the loops. So or the widths of the loops. Over what kind of sizes do you think these processes are happening? Because Anna Maronushenko's put forth this idea that maybe the corona is not structured in these neat loops, maybe it's structured in these curtains. So, but the fundamental block over curtain would still be something like what you would call a loop. What's your opinion on that? Like how do you think the ideas you're putting forth could be integrated into this new paradigm that Anna's proposing? Thank you.
Yeah, the second question about the sizes. I mean, the widths. As I said at the beginning, maybe the spatial resolution is not enough to really disentangle the smallest scales. So I don't think we can give an answer to this based on the observations, right? And then the first question was about, oh yeah, the V shape. You're right. It's a matter of density. I mean, if you put a not too dense blob, it follows slowly. Mm-hmm. If you put a denser blob, it follows quickly, and more dense. I mean, denser blob follows still quicker.
Right.
Just a matter of density. This, as you said, you can have a very weird blob, and then different parts will follow in different ways, only depending on the density.
But however, a lot of the simulations you're shown, they're basically that they don't have like, even though they're done in some dimensionality, they're still sort of that they can be scaled, to any size that you need. Okay, thank you.
Mm-hmm.
Piotr again.
Yes, one more question. What is I understand that this blob is like a part of magnetofluid which is separated from the rest. So what really defines it topologically? Is it like a surface of constant entropy or some other invariant? What defines the blob?
You mean in the numerical simulations, or
Yeah.
generally?
No, in the numerical simulations. Because I believe that the numerical simulation tends to approximate the real problem. So, there has to be some distinction. You see, like for instance, in atmosphere, when you have a cold blob falling or hot blob rising, the topology is defined by the surface of constant potential temperature, which is surface isentropic, basically. So this is my question. What defines thermodynamically, what defines the blob?
Okay. So I think you have told me. Nobody has thought of a blob this way. Normally, we look at the density, right? Say the 1D cut I showed before with a Gaussian profile, and then we say this is the blob because we are looking at the density.
Density only defines topology of the fluid for incompressible flow, because then you have the d rho dt is fixed along the flow trajectory. But in general case, when you have compressibility, it's not so easy. So now I have another question. Sorry if I am taking too much time. So let's say that this blob somehow separates from the rest of the fluid to make an entity. And so if it does, then it should also contain separate magnetic field lines, right? So if this is the case, can I think about those drops, right? Falling drops as those spherical lightnings?
Spherical lightnings?
Yeah, there are those mysterious, they are observed, the lightnings which are like a sphere, right? Some people saw them, some lived through it, some didn't. So is it something like this?
I don't know. I cannot tell. I'm sorry. I don't know.
Could it be?
I don't know what these lightnings are, really. So,
no, really?
Yeah.
You don't know about the spherical? Maybe it has a different name in English. I am translating from Polish.
I read it in Tintin books.
Yeah, but they are real. I know that they are observed rarely, but they are.
Ball lightning, someone said. Yeah.
Yeah, ball lightning. Okay.
So, but I'm sorry, but I don't know anything about them. As I said, I only saw them in a cartoon when I was a kid. That's all.
It's very interesting.
Any other question for Ramon? Phil?
Thanks so much for a fun talk. You summarized the 1D dynamics very well. So I think one of the takeaways for me is that if you look at one of your loops that's initially quite warm, so you're looking at active regions here, and if you look at one of those and it's initially, say, 2 million degrees, it's going to take on the order of an hour to half an hour to cool. And so the result you've got is that I think that you've got some source of heating which is going on, which can have frequencies much higher than half an hour, but it can't be much lower than half an hour. Otherwise, you drain out the corona completely. And that's sort of what we see with post-flare loops. And post-flare loops are just, I think, a phenomenon where a lot of energy goes into the flaring corona, and with that comes lifting of mass against the potential field. So you have a lot of mass up there, and then as the magnetic field relaxes to a more less energetic state than the post-flare loops, but they last like a day for some reason. So it would be interesting to know. I don't know if there are observations of post-flare loops which oscillate on the periods you're finding of several hours, because that period is much longer than the half-hour cooling time. So it suggests to me that there really is a heating mechanism going on periods of somewhat less than half an hour. And if I look at the physical pictures in terms of plasma physics, things like small-scale fast reconnection, interacting wave to generate nonlinearities, these are all going on really short timescales, like timescales associated with 1/10 of the Alfvén speed. So something like, really, really fast things. So I think what maybe you're seeing is a combination of all kinds of small-scale things going on, which are required to dissipate ordered energy of the magnetism on tiny scales, and that amounts to a small-scale kind of boiling away in the background of the energy from the large scale into the small scale. And then eventually that adds up on average to look fairly smooth on like a few hours time scale, so that you end up with a picture that's maybe compatible even with Parker's picture of the reconnecting tangential discontinuities, as well as the other modes like wave modes and what have you. So I'm pretty happy you found these, and I would love to know. I have a question that I think would be interesting to know the answer to. First of all, do you see them in post-flare loop phenomena, where you're in a slightly different situation? Secondly, even in the open field regions. So if you could observe 191 and maybe helium in some of the coronal holes, it would then be very interesting to see if you get the same, anything like the same kind of phenomena. I realize the temperatures are much lower, but nevertheless, it may be possible by co-adding things over, say, an hour now that you've got the time scale, you could co-add a lot of AIA data over an hour just to see what there is in these other areas of the sun, and thereby look at closed field regions versus open field regions as well. That would be really interesting to see. It may not yield anything. It may be hidden in the background or something. Anyway, I really enjoyed the talk, and congratulate you on a very nice analysis.
Oh, thank you. Thank you. What I wonder is, in the case of the open field, how important is it to have closed field lines from I mean, thinking of the simulations, which I don't know, I mean, from the physical point of view. So yeah, it'd be nice to check this.
Piotr, did you have another question?
Yes, the last one. I won't bother you anymore. So let's assume that the model that you have a heavier density fluid parcel falling down into the medium that whose density increases. That at some stage it has to stop and oscillate with Brand-Weissala frequency. What is the Brand-Weissala frequency in this problem with respect to density?
I do not know the Brand-Weissala frequency, but what I don't know is that what you're saying is that the mass is pushing down.
Yeah, it's falling down because it's heavier, right? And then it gets to the point when the environment is of the same density, but it has inertia, so it starts bouncing, produces gravity waves. So that if it happens that the frequency, maybe these oscillations that you see have something to do with the gravity waves, that they may be excited by the gravity waves.
You mean the oscillations, the long period oscillations?
Yeah.
But they are a different issue. I mean, they are controlled by the thermodynamics. But in this case,
the gravity waves are also controlled by thermodynamics.
Yeah, well, yeah, you're right. But what I mean thermodynamics, I mean by the interplay between cooling, heating, and the thermal conduction, which happens in the top of the apex, in the top of the loop. But then what you're saying is what happens when it collides with the chromosphere. I mean, when when the densities are comparable, this is
Yeah,
when the coronal
it
rain
starts
reaches.
oscillating.
Yeah, and then this has not been observed. And this is quite important, you know, to see what happens then. In the case of coronal rain, in other cases, it has been observed like one eruption sends off material and it falls down. And this would be more or less the situation you are considering now.
Why do you refer to this in a language that implies phase changes? Because condensation, right? So what phase is changing into what?
This is an abuse of language. Period. You're completely right. I mean, there is no evaporation, no condensation. It is a plasma, which is at the chromosphere, and it's simply because of heating, it's going up. You know, it becomes hotter and less dense, but there is no change of phase. And this is called evaporation.
Mm-hmm.
And then when the material kind of collapses, this is called condensation, but there is no change of phase. It's just change of temperature and density. You're right.
Okay, thank you very much.
Mm-hmm. Welcome.
Any other questions from audience? Okay, if not, then we thank the speaker again.
Thank you very much.
And thank you, Ramon, for keeping yourself awake until late night there.
Oh, it's okay. It's not yet time to go to bed.
Okay, thank you very much.
Thank you.